So I'm very curious to learn about this afternoon's granular flow talks and granular materials. Our first speaker, Jim Jenkins, will talk about fluidity, anisotropy, and velocity correlations in collisional sheared suspensions, and I'll give you a 5-minute warning.
Okay, great. Thank you, Norm. Maybe to begin with, I should say that no bacteria or fruit flies were injured during the course of this research. I'm going to try to be quick. I'm addressing a topic that's been mentioned several times during the course of the meeting, and that is a notion of fluidity introduced by Ken Cameron to describe granular flows, in particular dense granular flows. And this fluidity, which is denoted by the letter G, is the product of the shear rate, the pressure, and divided by the shear stress. So these are indicated here. And I want to show the relationship between this fluidity and the kinetic theory. As was mentioned earlier, Cameron's introduction of this quantity was criticized because there wasn't an interpretation of the physics behind it. And now I think he's gone a long distance towards relating the fluidity to the measures of the strength of the velocity fluctuations. Okay, so here is a numerical simulation that he carried out along with a graduate student at MIT, and what he did was make the fluidity dimensionless with a measure of the strength of the velocity fluctuations of the grains. And he's looking at a system in homogeneous steady shearing, simple shearing. And, well, I should say that in fact the simulations that they carried out were even more complicated than that system. It included inhomogeneous flows between bumpy vertical walls, shearing between bumpy horizontal boundaries in the presence of gravity. So I misspoke. That is, they simulated a wide range of collisional flows with frictional spheres and frictionless spheres, and they plotted the results against this dimensionless measure of the fluidity. That is, the fluidity divided by strength of the velocity fluctuations. And they've obtained a remarkable collapse of the data, indicating that the fluidity has much to do, or everything to do, with a measure of the velocity fluctuations in their flows. That is, when fluidity is normalized by this strength, all the data over a wide range of volume fractions collapses. Doesn't collapse perfectly, for example. So here are the red X's. They look like they might be going singular at a slightly different volume fraction than the rest of the data. But those red X's were rather frictional particles. So there is some sensitivity indicated even on this figure to the properties of the particles themselves. Okay, so that's fine. That's about as far as Cameron took it. That is, and Diego Berzi and I then asked the question of, can we predict the fluidity over a range of volume fraction using existing kinetic theories? And in order to be somewhat more precise, we restricted our attention to simple shearing flows, that is dense, steady, or not dense, steady, homogeneous shearing flows of frictionless spheres. So we did the simplest possible system first. And I'm going to depart from the notation that was in that Cameron's figure. I'm going to denote diameter by sigma, the density of the material spheres by rho, the density of the material of the spheres by rho p, volume fraction by nu, and coefficient of restitution by E. And then the constitutive relations of kinetic theory have this structure. The pressure is a function we call F1 that is a function of volume fraction restitution for frictionless spheres, and perhaps a dimensionless measure of the shear rate. And similarly, the shear stress has a slightly different structure. It's proportional to the shear rate. It involves dependence upon our measure of the strength of the velocity fluctuations, called the granular temperature, and particle diameter. So the fluidity, or the dimensionless fluidity, is then just a ratio of these functions. And we're going to be interested then in characterizing the ratio of these functions in the context of kinetic theory. And to do that, we're going to introduce this dimensionless measure of the shear rate. So that's capital R. And here's what you get when you compare the predictions of two kinetic theories with the results of numerical simulations of simple shear flow over the entire range of volume fractions. I should say that the data we saw of Cameron's was from about 49% to 64%. So Cameron, in fact, is focused on applying his theory in this range. We thought we'd see what the kinetic theory had to say about fluidity over the entire range of volume fraction. And we used two kinetic theories, one due to Garzo and Dufty, which is linear in the velocity gradients, and that does pretty well. And a second by Saha and Alam, somewhat more recent, that is nonlinear in the velocity gradients and takes into account anisotropy of the velocity fluctuations. So it's a theory that has a, more complicated, perhaps far more complicated structure. And you see that does remarkably well, except as we approach random close packing. Okay, so I'm going to focus attention on the Saha and Alam theory, although the Garzo and Dufty theory is the one that's used most often because of its relative simplicity. And I should say, Saha and Alam did not intend their theory to be pushed beyond 49%, and I know Garzo is surprised that their theory is doing as well as it does at the concentrations before 50%. So by extending these theories into the denser regimes, we're abusing their intentions, but I wanted to show you how these theories predicted all the way up to 64%. Okay, and here, in terms of the Saha and Alam theory, are these functions that appeared in the structure for the pressure and shear stress. And I first should say, so here is the radial distribution function of contacting spheres, and that has a singularity at 60 random close pack for frictionless spheres. So that appears in these dense constitutive relations. And now from this point on, I'm going to be focusing on what's happening up here. Eventually, I'd like to explain that drop that is observed in the simulations. That's not captured by either one of these kinetic theories. Okay, so Saha and Alam have a nonlinear theory. R, remember, is that dimensionless measure of the shear rate. Eta is a function that is associated with the fact that they incorporate or admit the possibility of the velocity fluctuations differing in different directions. So the velocity fluctuations, rather than being isotropic as it is in most kinetic theories, they include a measure of the anisotropy of the velocity fluctuations. And eta is the in-plane anisotropy of those fluctuations. And here then is the function F2 of the stress. So the point is that there is rate dependence in F1 and F2, and also a dependence on the anisotropy. And what I'd like to do first is I'd like to, again, focusing on the theory of Saha and Elam, I'd like to explain why their theory gives a constant value of the dimensionless fluidity in this limit, and that allows me to introduce some of the equations that I'm going to need in order to try to explain the dip. So here is the second moment of velocity. Capital C is the fluctuation velocity, and we're in principal axis coordinates here, and you see that eta characterizes the difference of the in-plane fluctuations, and lambda squared is the outer plane anisotropy, and it really doesn't enter into the calculations that we'll be talking about. And as I said, I'm going to focus my attention on dense flows, volume fractions greater than 49%. And now I'm looking at the more complicated balance equations that are required when you're introducing the full second moment of the velocity fluctuations as descriptors in the theory. That is, usually you only have the trace of the second moment, which is what we call the granular temperature. Okay, so you've got a balance equation. We're just focusing now on describing what's happening in the plane of motion. You've got a balance equation for the in-plane deviatoric stress, and that balance between those components of really the collisional stress is balanced by a collisional production term. And Saha and Elam provide the constitutive relations for these quantities, and they're given in terms of things that we've introduced before, in terms, at least notationally. So this is the sum of the in-plane stresses, collisional stresses, and this is the difference of the productions, collisional productions of this particular component. And I want to note that, the collisional production involves the measure of the shear rate, dimensionless. I'm dimensionless all the way through here. The dimensionless shear rate, a measure of the difference in the in-plane principal components of the stress, and the temperature itself here, the trace of this tensor, and also the particle diameter here. So it's important to keep in mind that the particle diameter is appearing in the denominator of this expression for the collisional production. So that's one balance equation. Why do we introduce these balance equations? They serve to determine capital R and eta. So that's what we're trying to do. That we have in this simple flow that's steady and homogeneous, we have algebraic equations. The balance law is reduced to algebraic equations for the determination of R and eta. And so similarly, we have a balance of the trace of the in-plane components. And again, we have the expressions for the difference in the collisional stresses provided by Saha and Elam. And I should say I'm truncating their expressions and retaining terms that are at most quadratic. Okay, so and we have a collisional production of that trace, and that collisional production also includes quantities that we've talked about, R and eta, and the particle diameter. Okay, so now I want to indicate that these balance equations are satisfied by R and eta in a way that gives the dimensionless fluidity as a constant. So I'm explaining that plateau in their data. So the solutions to these two balance equations give eta as a linear function of R involving the coefficient of restitution, and using that in this equation, the second equation, gives a quadratic equation for R. And the important thing here is that quadratic equation for R is independent of the volume fraction. Okay, so because that's in the equation for R is independent of the volume fraction, that means that neither R nor eta is a function of the volume fraction. So, forming that ratio of F1 to F2 gives us a ratio that does depend upon eta R, but it's in a way that is independent of the volume fraction. So that means that the dimensionless measure of the fluidity in the dense regime, according to Saha and Alam, is constant. Okay? Well, that's not what the numerical simulations see. Okay, so let's try to understand and perhaps repair that defect. Okay, and we would claim, Diego and I would claim, that what's missing is an incorporation of velocity correlations, if you're dealing with rigid particles, or perhaps multiple collisions and the development of clusters, if you're dealing with a soft particle simulation. And the way that in the past that we've taken that into account in the constitutive relations of simpler kinetic theories is to introduce a length scale different from the diameter that determines, let's say, let's talk about size of clusters, or we could talk about lengths of force chains or regions of velocity correlation in the flow, and that this length scale is determined through a competition between the ordering effect of shear and the randomizing effect of collisions. And there's a coefficient that we determine in numerical simulations. So looking at numerical simulations and interpreting them using the Garzo-Dufty theory gives us a characterization of the volume fraction dependence that we're comfortable with over the range of volume fractions between 49% and 64%, and also that we get a complicated dependence on coefficient of restitution entering through a coefficient. Okay, so we're going to adopt that length scale, and then the question is, how do we employ that length scale? And in the simpler theory, we employ that length scale to replace the diameter in the rate of collisional dissipation of energy to replace the diameter that appears there with that length scale. So we use that length scale in the simpler theories in the rate of collisional production, or, well, in fact, it's collisional dissipation of energy. So the way we're going to use it here is in all of the collisional productions of second moment, we're going to replace the diameter by this length scale. And so here is the expression for the collisional productions of the two combinations of moments. The right-hand side of the two equations of balance that we looked at before, everything is the same except where sigma once was, we replace it by L. Okay, and again, here is the definition of L in terms of our measure of shear rate and this function of volume fraction that is singular at random close pack. Okay, so if we do that, we obtain different balance equations, algebraic balance equations for the determination of R and eta. And taking the dominant terms of these equations, the equation for R is as you see it, and the new feature is it has this function that appears in the new length scale. It has that function in the denominator. And the ratio of eta to R, based upon the new solution, is proportional to this function that becomes singular at random close packing. So the result is the dimensionless fluidity now has this structure, and as the volume fraction approaches random close packing, these terms in the numerator disappear, and this term in the denominator goes to infinity, because this term goes to infinity. And as a consequence, we generate the dip in the dimensionless fluidity in the limit of random close packing. So the message of this part of the story is that the introduction of this correlation length in the collisional production permits the theory to reproduce the behavior of the dimensionless fluidity over the complete range of dense volume fractions. And I think I'll stop there. Thank you for your attention.
Microphone's on, and let's just start here, and we'll work our way up. Okay. So, no, please, Joe.
Jim, their theory has a divergent length scale when you approach yield. So how is that accounted for in this treatment?
Well, for frictionless particles, the yield is at random close packing. So we have a singularity at yield.
So everything you can do here depends on it being frictionless, having zero.
Well, we can repeat the calculation. However, in the context of this theory, the singularity for us is always going to remain at random close packing. Okay?
So you would insist that that's the only point where you have yield.
Well, then there's an issue of yield that, what we see, so I should say.
Well, yield is based on dilatancy.
Yeah, but so maybe I can say.
Jim, we might need to repeat the question for the audience. I'm not sure everyone back.
Okay.
Maybe you can recap the discussion.
Okay, so so Joe remarked that the Cameron theory involves a singularity that takes place at yield. That is, I guess that would be the limiting point of the mu-I rheology, for example, at I equals 0. Yeah. And the question is, do we repeat that? Is that feature in the theory I just talked about? And the answer is yes for frictionless particles. So now what's the issue for frictional particles? So let me. Okay. So for and we're convinced that this length scale L that we've introduced is singular only at 0.64, no matter what the friction coefficient is. Okay, and in the context of the kinetic, well, that's another issue. That is, everything I've said is applicable to systems that are interacting through collisions. And this limit of I equals 0 is a limit where stress chains are completely spanning any flow. It's really some elasticity in place. So I don't pretend that this collisional kinetic theory applies beyond a certain value of I. Okay? So that's just a qualification. But let me say here that, so we're saying that L is singular only at 6,4, but the radial distribution function at collision, as friction increases, becomes singular at values of volume fraction lower and lower. 0.6, for example, 0.58. Okay? So the kinetic theory has both of those singularities in it. Okay? But I wouldn't presume to push the kinetic theory to yield. So, okay.
So our next question from John
Yeah,
Brady.
so, is this working? There also, if I recall, in the Cameron theory, there's also a length scale that appears for the diffusion of fluidity, basically.
Yeah.
And what is the connection between that length scale and your capital L?
So I would say Cameron's length scale is L, but Cameron would say it's a length scale that becomes singular at yield. So I think there's still that difference to be resolved. And as I say, we can't push our kinetic theory anywhere close to yield. We need collisions to be transferring momentum.
Right, but in this theory, you didn't discuss any aspect that you'd have a Laplacian someplace in the description.
Did I have a what?
You'd have a Laplacian of
No,
yeah.
this is simple shearing flow. Absolutely. So this is homogeneous. However, now that we've identified, or Cameron has identified, fluidity with the measure of the velocity fluctuations, we say, well, we can map his theory into our kinetic theory, and his non-local equation is our energy balance. Okay, so that's the correspondence now that we feel able to make.
And so then there's a conductivity of energy in the energy balance. Which
Yeah, absolutely. Yeah, there's diffusion of energy, conductivity of energy, absolutely. Yeah, and we have boundary conditions that, in my view, Cameron and his colleagues are struggling a little bit to formulate.
If I could ask a follow-up question to the question of the length scale. So in this theory that you're using, you have a fully anisotropic fluctuation spectrum.
Yeah, in Saha-Nalam's theory,
Right?
yes.
And so you also have, I guess, anisotropy. You have length scales that are going to be also dependent on direction. Is that
Well,
the case?
we're introducing a single length scale here.
Well, that was I was asking,
Yeah,
right?
I mean, right,
Okay.
we can complicate this as much as we like.
Okay.
I mean, in fact, so when I told John that we're putting Cameron's theory in correspondence with the kinetic theory, it's not the Saha-Nalam theory we're putting it in course. It's the Garzo-Dufty, because it's linear in the gradients. It's a more familiar theory. Saha-Nalam, generated to inhomogeneous flows, is a far more complicated theory. It might be the appropriate one, but complicated.
So we have a question here, but while we're getting to that question, my quick follow-up is, if we take physically meaningful this length scale, and you alluded to the force chains that Natalie showed us so beautifully in her simulation or experiments or images of that, would one then expect this to be a measurable length scale through such techniques? Could one look at that way?
Diego Berzi and his student Vescovi have measured the length scale in a simple shearing flow of I think both frictionless and frictional spheres.
Okay.
Yeah, so it's been measured.
And that somehow corresponds to the length scale you're calculating.
Yeah, exactly.
Okay,
I mean, it corresponds exactly to
okay.
that length scale.
Great. Next question.
So, Jim, I think I missed, but I assume your length scale is not really very much dependent on phi when you're close to the dense regime, isn't it?
Say this again, it's what?
In your theory, the correlation length is independent of the packing fraction.
No, the length scale is singular as you approach the It depends upon the
there's a
volume
difference.
fraction, like 1 over 0.64 minus volume.
see.
So it's singular.
So
That's
how you
what's
have it.
giving us the dive in the dimensionless fluidity.
Okay.
That singularity.
Okay, thank you for that clarification. We have one more question here. Mr. Shaw.
In yesterday's talk, Prabhu Nath was talking about Cameron's theory, and he was trying to get his length scale through his size of the volume over which he was integrating. And so which one is the more appropriate mapping? The one that you are doing to his length scale, or the one that Prabhu was talking
Well,
about?
what do you expect me to say?
Prabhu's not here to defend himself.
Yeah, exactly. Let's just pass on that question.
We'll wait till he comes back. Okay. Well, great, that's a good discussion point for further discussion. And if there are no other questions, then let's thank Jim for a provocative talk. Thank you.